Thanks for staying for the last talk. You've heard quite a bit throughout this conference about radio observations on the far side of the moon that enable some cosmology and astrophysics investigations. Actually, the moon enables a number of opportunities in astrophysics, one of which is not the focus of my talk here, is there is a unique observational window roughly around TeV for astrophysical neutrinos that we've done some work on. But what I want to spend some time on here is talk about another mission that's uniquely enabled by the moon in MEV or nuclear astrophysics, and it's called LOCO. I'm not going to spend too much time on motivating the science. We have a poster here, and I'm probably going to run out of time. But let me cut to the chase here. MEV, or nuclear astrophysics, the regime from roughly about 100 keV to about 10 MeV, is perhaps the last electromagnetic regime without a sensitive sky survey. At lower energies, somewhat soft X-rays or hard X-rays, hundreds of thousands of sources. At higher energies, GeV or higher, we're now getting hundreds of sources. This intermediate range, there is a dearth of sources. We know they have to exist. It's a very interesting, complicated region of the spectrum to do astrophysics in, but we haven't been able to do it. This is a very busy slide. I'm going to extend what Jack said this morning regarding the decadal survey. There are a number of elements in the decadal survey, time domain astronomy, the detailed understanding of type 1a supernova progenitors, the explosion mechanisms, etc., the cycle of matter and energy in our galaxy. There's a wide range of very interesting topics that we can tackle in MEV astronomy. And the question that you're asking now is, okay, if it's such a hot thing, why hasn't anybody done it? Well, we did do it. In the 90s, we had the Compton Gamma Ray Observatory. One instrument on GRO was CompTel, working from 1 to 30 MeV. I worked on that project. To take it to the next level, to get the next increase in sensitivity and performance, there are limitations given our current budget situation in cost, and also the technology drivers that are required to take us to the next level. The project that I'm going to talk about today, LOCO, mitigates those problems and I think represents a new opportunity for us. Thinking a little bit outside the box, LOCO utilizes two unique things. The first is occultation imaging, which I'll tell you about in a second. The key benefit of occultation imaging is that it eliminates the need for a large position-sensitive gamma ray spectrometer, which lowers cost and complexity and mitigates the technology development efforts that are required. The second is that we're utilizing the moon as a scientific platform, utilizing the unique lunar environment to enable science that can't be done anywhere else. So if you ask questions, I'll tell you about that little triangle thing sometime. What is occultation imaging? Occultation imaging is really using temporal modulation to get at the imaging or the location of sources on the sky, as well as their size if they happen to be extended. Imagine for a second you have a spacecraft in orbit about an occulting body. In this case, of course, it would be the moon. And you have a distant source. As the spacecraft orbits the occulting body, taking data on a fixed cadence throughout its orbit, as the source comes within the field of view, or with respect to the spacecraft, rises over the limb of the occulting body, you get count rate increases. As the spacecraft goes around the back of the occulting body, it eclipses that source and you get count rate decreases. If we know the ephemeris, the position of the occulting body, and the spacecraft, you actually don't need to know the position. Let me say it differently. You can determine the position and the existence of that source by identifying these occulting features. In fact, what's most important, where all the information about that source exists, is in count rate differences. Actually, that's a mistake. Count rate differences, converting that time series to count rate differences, where we take the difference between a previous cadence interval and the next interval, and a source exists where we have large count rate differences. Now, we can determine the significance of these spikes. We can identify that there is a source, but that doesn't help us with imaging. And part of the mission here is to do a sky survey to build up a catalog of the hundreds or thousands of sources that we anticipate seeing. So this argument here, time series analysis alone, can only tell us if sources exist. And in fact, this isn't all that mysterious. Similar techniques are being used on Kepler right now to look for transiting planets. We turn this around. Kepler doesn't have knowledge of the occulting body and uses the time series data to identify that. We turn the problem around, and with knowledge of our telescope and the occulting body, try to identify these sources. So how do we take these time series data to do imaging? Well, at each point along the orbit of the spacecraft, I'm acquiring spectra. Think counts. I'm acquiring spectra on a fixed cadence. And if a source comes into the field of view, if I get a count rate increase, I know that that count rate increase could only occur if a source was rising somewhere along the limb of the moon. Now, this alone doesn't tell me where that source was rising, but it tells me it was rising somewhere along the limb of the moon at that particular time. If I take the limb of the moon, the position of the limb of the moon at each time interval, and project it on the celestial sphere, I get an image like this. This, of course, is simulation, where each little slash here, it's a little hard to see in this room, is the position of the limb at a particular time interval. I can also make a template. If I assume a source exists at a particular location on the sky, I can ask the question, when would that source be visible? Which lunar limbs would exist in my subset of data to think of this as a point spread function. These are the collection of limbs that would produce a signal from a source at that position. Because the spacecraft precesses throughout its orbit, this is a day's worth of data, the spacecraft precesses, so the orientation between the spacecraft, the moon, and the source changes slightly, and so the locus of these intersecting limbs is the location of the source. So I can ask the question, does this template exist in my data? And of course, I've amplified the signal so you can see it with your eye, but that doesn't have to be the case. I can do a correlation here to answer that question, does this shape exist in this chunk of data? And the answer, of course, is yes. This correlation analysis is relatively straightforward. Currently, we're using a brute force method to Pearson R with Fisher transformations and ultimately getting confidence intervals on the location as well as the significance of the source, although this can also be done with Fourier transforms and more robust techniques, but we're having quite a bit of significance here. The other unique feature of occultation imaging, or at least loco-based occultation imaging, is that what I call the point spread function, you saw this one in the previous picture for a source, in this case at the location of the crab, but this point spread function is unique to the location of the source on the sky. And people have identified that as a hit against occultation imaging. We're using that to our advantage. The fact that the point spread functions are different no matter what the source location is on the sky enables us to do parallel searches for sources in our data sets very effectively. Data we take on this fixed cadence are acquired spectra. So we can take these time series, we can slice them up by energy, we can slice them up by individual lines, aluminum 26 line at 1.8 MeV, just as an example. or we can do broadband spectral searches, making time series any energy slice we want. The template that I showed you before for each source on the sky is independent of the energy. It only has to do with geometry. And so I can do a simultaneous search for sources throughout my visible sky at all different spectral individual lines or broadband spectra, and simultaneously look for these sources. So this analysis is highly parallelizable and can be used for both identifying point sources, getting their variability, their significance, and their spectra, as well as extended sources like the extended galactic emission that we also know exists. Now, why do this at the moon? Okay, probably easier to launch into Earth orbit. Well, this actually has been done in Earth orbit at slightly lower energies, going up to slightly less than 200 keV. The BATSI experiment aboard CGRO, which was 8 scintillator detectors on the corner of GRO, did this as a secondary mechanism, technique for identifying sources. But because of the Earth's atmosphere and the Earth's magnetosphere, it severely limits the capability of occultation in Earth orbit. Going to the moon, we have dense regolith, which gives very sharp occultation features, translating into very good localization. No lunar no lunar atmosphere to speak of, which means we have no differential absorption like we do on Earth, and no magnetosphere, at least for us, which means well-characterized long backgrounds that vary on long time scales, which means we can integrate for a long time and gain source sensitivity. So let me jump ahead a little bit, went a little long. One of the technology drivers is power for our mission, and so we've been working on silicon photomultipliers. We have another poster here. This was in part supported by the Lunar NLSI. We've had great success working with an industrial partner developing these silicon photomultipliers for our gamma ray spectrometer, and in fact using a very inexpensive inorganic scintillator and combined with these silicon photomultipliers, we are achieving an energy resolution of less than 3%, which many thought would not be possible. It is absolutely possible, and we're doing a great job. And I advertise this here because it's not just useful for our purposes for LOCO, but this could be used for planetary orbital geochemistry, exploration of asteroids, etc., where gamma ray spectroscopy is important. These devices require only a 30-volt bias. They're very rugged, insensitive to magnetic fields, and are fairly rad hard. We have a strong program that's ongoing now to evaluate trade-offs in the design of our mission. I don't expect you to read this, but because we have interest in solar physics, the solar flares, for example, where there's some lunar science that we can do, and the primary science driver being astrophysics, we are currently evaluating how these trade-offs impact the design of our mission. And finally, let me just throw this up here. LOCO is an Explorer class mission, probably not a SMEX because of the mass that needs to be launched, but it is certainly an Explorer or a MIDEX class mission. It spans the MeV energy range to meet our science goals, less than 4% energy resolution, which we are currently achieving, half an arc minute position resolution, which in gamma ray astronomy is crazy good. It would need to be a fairly large experiment, approximately 1 square meter of instrumented area, which would be about 400 kilograms in our current design, and would go into lunar orbit at about 100-kilometer altitude, although that's one of the trade-offs that we're currently evaluating. And here I show the baseline LOCO sensitivity curve compared to CompTel and 2 other instruments, IBIS and Integral, both on the Integral. Okay, thanks.
Very good. Thank you, Richard. Very exciting mission, I think very important. Unfortunately, we are out of time, and the Dragoons are here to drag us back to the ballroom because we have some very important student presentations in there. So